Hi everyone. In today's video, we're going to be discussing modern data centers and why we land and how we landed in a Clos VXLAN EVPN and when L3 is a pure win. Every major cloud provider's trading floor AI cluster today runs on the same core idea, a Clos fabric. But why and how did we end up here? EVXLAN with BGP EVPN gives us layer 2 at scale. Why do some shops still need a pure layer 3 fabric instead? In this video, I will map the evolution from a classic 3-tier data center to a layer 3 leaf and spine fabric or a layer 2 leaf and spine fabric, show how VXLAN EVPN actually works and why and when you need a layer 2 fabric and when you should still and when and why you should still keep it simple with the layer 3 only. So today's agenda is what modern data centers mean in 2025, the evolution, meaning from the traditional tier 3 to leaf and spine class network. Then we'll discuss layer, underlay and overlay and why class fabric scales. We will discuss a VXLAN with BGP EVPN, where the VXLAN is the data plane and the BGP EVPN is the control plane for L2 and L3 overlay. While we still need a layer 2 fabric sometimes. We'll be discussing that because there are instances whereby you need to keep a layer 2 fabric or a layer 2 adjacency between different hosts. We'll also discuss instances whereby we need a pure layer 3 fabric. Then we'll discuss design flows, pitfalls, and operations. If you're designing an AI or a machine learning cluster, a trading network, a private cloud, and a hyperscaler, if we are working with an hyperscaler, this will help you decide what to do and why. So let's get started. A modern data center is a service fabric, meaning the compute, the storage, the accelerators are populated and stitched together by a network that prioritizes three things: the throughput, the predictable latency, and the failure isolation. These three things are very important in our modern data center, be it a data center that is being used, a fabric, or a pod that is being used for training AI and machine learning models, or in an hyperscaler where throughput and you also want a predictable latency, and you want to minimize your failure domain. Oh, in this kind of fabric, you're more interested in east-west traffic, even though because most of the traffic are limited to the data center. There are instances you also need to take into consideration north-south traffic, how traffic is moving from that particular pod to another pod or to the internet. In an hyperscaler environment, there could be instances where traffic is coming from the internet to either reserve a virtual machine or reserve an EC2 instance, or in a training environment, there are instances where traffic is just moving across the different GPUs, or in a storage environment, there are instances where traffic is moving across the storage clusters. Horizontal scaling beats vertical scaling. It's not every time you have capability or the ability to move from a, a smaller chassis to a bigger chassis. So you may then be limited to just adding more switches or more routers, which is basically what we call horizontal scaling. Automation is very important in this kind of environment, especially when you're dealing with thousands of switches or thousands of routers. It is so unrealistic to think you will deploy configuration on these devices manually. You can't just start banging your keyboard and doing config T. Multi-latency is very important. Multi-tenancy is very important thing to consider, especially when you're in a particular environment and you have different customers using your servers connecting to your leaves. So yeah. So let's talk about the classic three-tier network. In the classic three-tier network, you have the access layer, the aggregation layer, and the core layer, which is basically and most of the time built for a north-south traffic flow. In this kind of setup, you need you're talking about big chassis, you're talking about spanning tree to avoid loops, because between your distribution and your access layer, or your distribution like aggregation and your access layer, they are basically layer 2, and your default gateway for your servers is going to be located in the distribution layer. And you're talking about spanning tree, we're dealing with layer 2. So you are not going to be able to utilize all the available fabric. So, like an example, if you look at this on the screen, this is a tier 3, this is a Clos environment. Let's assume this is a layer 2 environment, and we have the leaf and the spines connected to each other. There is no way we are going to be able to use all the available links. Then that means we will only be, for example, we will only be using all links connected to spine 1 for traffic, while all links connected to spine 2 will be blocked until you have to avoid to prevent loops. Then that way, if leaves, so for example, if connectivity for leaf 1 to spine 1 fails, then leaf 1 to spine 2 will then come up, because spanning tree will have to calculate we have to recalculate and then get that into service, which is never optimal. Yeah. As we scale over, subscription is going to get ugly for sure, because you have to then consider how you're going to add more capacity to the fabric, which is going to be a pain. Spanning tree is going to be all block your links, and deterministic bandwidth between the two layers are never going to be guaranteed. So here comes a Clos fabric, where your leaves are connected to your servers and the spines connect to the leaves. In an ideal case, no leaves connect to, in a default case, let them say an ideal case. In a default case, no leaf connect to the leaf. But as you can see in my screen here, you see leaves connecting to leaves, forming a VPC pair. This is basically a scenario where we're trying to use a multi-chassis lag just to give us a switch level redundancy, where both switches are acting as one to the client they are connected to. The traffic lead takes at least at most two hops. That means it's going to go from the leaf to the spine back to the leaf in the tier 2 clause, making latency predictable. With ECMP, we hash flows across many links and unlocking horizontal scaling. So basically, you're going to be using all available links with ECMP for traffic forwarding. And if you want to add more fabric, if you want to have more capacity, we just need to add more leaves. Clos fabric thriving on a clean underlay. Truth is at layer 3 fabric, layer 3 IP fabric. So basically, looking at what you're saying on my screen there, you're going to have your leaf and spine connected to each other using an IP fabric. Anyway, that means we're basically kicking out spanning tree from our network. And I'll configure a point-to-point IP addressing. In this case, for spine 1, you have an IP address, your IP interface brief. So spine 1, you have point-to-point IP address to all the leaves. And we are running OSPF as our underlay routing protocol. We all know, as a network engineer, we all know what OSPF, I believe we all know what OSPF is. Knowing it's this kind of fabric. You can use different kind of routing protocol for your underlay. You can either use, which is not realistic, you can use static route. You can use OSPF, you can use BGP, you can use ISIS, you can use EIGRP. In this kind of fabric, we only have how many? We only have 6 leaves. But imagine a fabric where you have like 1,000 GPUs or 1,000 storage controllers or 1,000 servers. It's not realistic to use OSPF as the underlay because of the uh, number of LSAs that is going to be generated. And for each link failure, there is going to be a need for recalculation of your shortest path tree, which means that is going to introduce more routing convergence for each link failure. So if we're dealing in an hyperscaler or a very large fabric, it always makes sense to use eBGP for your underlay and eBGP for your overlay. So basically all your spines are going to be in the same ASN, autonomous system number, and all your leaves will have their own individual ASN. Yeah, this example we have here is with OSPF as underlay. In another video, I'm going to come up with a scenario where we are going to have BGP as our underlay and BGP as our overlay. But let's focus on this one where you have OSPF as our underlay. So we're using an IGP as an OSPF. So sure. So this is a Cisco Nexus switch. I see we have full OSPF is full adjacency between all the leaf and the spines. So OSPF is currently running. And one major thing I need to call out is a consistent MTU is very important in a VXLAN fabric because of the extra VXLAN overhead that's going to be added to your Ethernet ring. So it's going to get your layer two and header, and it's going to add a VXLAN header to it. You're going to get your layer two packet, add a VXLAN header to it, add a UDP packet, add an outer IP packet and an outer Ethernet packet. The total of extra overhead because of VXLAN is 50 bytes. So you need at least 1,550 bytes for MTU. In an ideal hyperscaler environment, it's better to just use a jumbo MTU, which is a 9,000 MTU, or some fabric will use 9,216. Some vendors will use 9,216. Vendors like Cisco, Juniper, and all that. So those are very important. So for a VXLAN cluster environment, the most important thing is the underlay. It should be there, which is basically layer 3, ECMP, and fast convergence. These are the three very important key for a cluster network. So underlay gives you the reachability between the loopbacks of the leaves, which is basically the VTEP. I'm not trying to go in depth with VXLAN. If it's needed, drop a comment and I can discuss VXLAN. But this I'm just basically having a chat around what is needed in our mother data centers and our design concept that we need to consider. But just to do a little touch on VXLAN and a BGP EVPN. So basically, in illustrative introduction, VXLAN encapsulates Ethernet frames in UDP, adding a VNI, which is a 24-bit segment ID. So we can scale to a 16 million segments. VTEP, which is virtual tunnel endpoint live on leaves. They encapsulate and decapsulate VXLAN traffic. Like I said earlier in the video, VXLAN is basically for data plane. And if you're using VXLAN by default, we're just having a giant layer 2 fabric. And for host behind each VTAP to learn about each other, there's just going to be doing the natural flood and learn, which if you're hosting a giant fabric like 5,000 servers, it's never going to make sense. That's just going to, the app flood and learn is just going to saturate the traffic. So we need a control plane. So that is why we came up with. So we could either use, we need a control plane. So we don't flood unknown MAC address across the fabric. And that is where we have BGP EVPN. It distributes endpoint switchability, so we don't do flood and learn, which makes endpoint switchability efficient. Control plane learning from both MAC and IP. So and the control plane learning is basically done with the different route tabs, which is route type 2, MAC/IP. So MAC host X is reachable via XY, enables reachability between both. You have route type 3 for multicast or ingress application info to build flood domain per VNI. We have route type 5 for layer 3 routing for inter-VNI routing tenant VRF for distributed Anycast gateway. So apart from routing route types. We also use distributed Anycast gateway. That means same virtual MAC or IP address on every leaf. Also use a local leaf as default gateway. So that will be, we basically have low latency and no tromboling. You have multihoming or ECI. So basically you have active server connectivity across two leaves. So if we say, yeah, so that way both a server, let's say for example, since server one, you can use both links for forwarding traffic. And EVPN handles designating the leave as the designated forwarder to avoid leaves. Oh, why do we sometimes need layer 2 fabric? If we think our layer, okay, if layer 3 is clean, why do we need layer 2 at all? Because majority of the time it's just because of the design requirements. So we will need live movability without IP change, which is very important for service like vMotion, live migration, legacy, apps at coding IP addresses that wants to keep a layer 2 adjacency, storage adjacency expectations. So for example, when you want your storage controllers in a particular cluster, they for sure need to be, and they need to be on the same, in the same VLAN or broadcast domain. Like for example, a NetApp controller backend connectivity for a cluster management need to be in the same layer 2 adjacency. So the cluster connectivity doesn't go through a layer 3 network. So you need that. You need layer 2. So if we say, so in an instance, we can then need, when a layer 3 fabric breaks VXLAN, there are compelling reasons to skip overlay and run pure layer 3 in a close layer, especially for greenfield cloud native workloads. Majority of the time, the reason why we will need a layer 3 is just for simplicity. We don't have to deal with the VXLAN complexity and configuration. Deterministic failover domain, no layer 2 loops, no flood domain, fault state, local routing converges faster. Lower overlay, you're not dealing with VXLAN, adding an extra 50 bytes at scale. That's MCU headroom, adding hashing behavior and NIC overload consideration. Container or Kubernetes first environment, workloads are already IP-centric, service meshes, and cost, which I believe that we are all used to in networking environments. Script, I'll start with underlay as leaf and spine and Clos using an layer 2 and layer 3. When you're making your design decisions, I think the things you need to consider, do I need a layer 2 stretch or a seamless mobility? If yes, then we choose like a VXLAN EVPN. Do I need a multi-tenancy with strong segmentation? If yes, then EVPN helps map VNI to VRF cleanly. If neither L2 nor every multi-tenancy is required, then a pure layer 3, it's simpler. No doubt about it. For AI and ML or storage intense cluster, ensure consistent MTU, QoS, ECN priority flow control as needed, and any gas gateway if you deploy overlay. Across all options, invest in automation, telemetry, and testable failure scenario. So we've talked about the design consideration, the different technologies. We're talking about deploying and all that. So let's talk about operations, which I believe it's everybody's 98 day two environment, rapid fire, something is going on in the network, you need to fix it. Things to consider: a standardized MTU, either 9216 or 9000 end-to-end when using VXLAN. Consistent hashing ECMP across vendors and avoid entropy loss. Proactive telemetry, stream interface counters, drops, buffer occupancy, EVPN route, app or neighbor discovery rate. Or when doing your change, you always make sure that the blast radius is controlled, stage by stage, test, drain, and restore. Document your control plane choices and security and segmentation. So let me just go through my topology here. So we have our leaf and spines connected, and I already demonstrated that we have point-to-point IP reachability. You can reach. So leaf one can already reach. So leaf one have the IP addresses, reachability to all the VTAPs, which is basically the loopback of all the leaves. So show IP route OSPF. So you see, this is the OSPF, and leaf two. This is the IP address of leaf two, which is yeah, we have reachability to IP address of leaf two, which we do for all of them. So once we have actual reachability for all the leaf backs, then we should have this is the NVA interfaces, and this is the source on the primary, and that's because we have yeah. So these are all the BNI. So I will talk about VXLAN in another video, where I will show you how to configure the underlay, how to configure the overlay, and the different troubleshooting we may need to do. So yeah, I just want to demonstrate that we have reachability between this, the host, the VTAPs, and we have reachability between the host server 2 and the external route in another ASN, which is basically this. And that's I'll discuss that in another video. This is my first presentation on this channel. Do well to like and subscribe. I'll be coming up with different discussion for network engineers. I'll be inviting different network engineers to the channel. Network engineers working in different hyperscalers, working on different incredible network designs, just to shed light on what our career looks like now in the current AI boom. How to make sure that we're still relevant, and how to always upskill ourselves to keep getting better in this field. So do well to subscribe, like this video to encourage it to serve an encouragement for us to keep doing more and to always keep getting better. So it's quite obvious that this is my first video. Not used to recording, but I think it's time to start giving back to the community, getting people up to speed with what we can use to keep ourselves relevant. Thank you very much for watching, and see you again in the next video. Bye.